My name is Lacey Amos-Scheuer, and this is my recording for the mapping demonstration for Genetics 1. And we're going to get started with me just doing a screen share where I've preset some tables on my Google Documents. And as I switch over here, I'm going to share my screen. Here we go. So as you can see here, why is it doing this? Go back here. All right, so up here, this is the raw data that the problem originally gave us. And usually step one is to start identifying the two parental genotypes. And a pretty easy way to do that is to organize it by size and to make sure that not one single genotype is taking up an entire greater than 50% of the population than any other of the genotypes. And so after we do that, you end up getting a table like this. And it's also wise to get a total of the entire offspring population, which we have here. Step 2, we go down here and you start to look at we start to want to identify the distance between gene A and gene B, with keeping in mind that the plus signs are referring to a wild type expression of that allele on the homologous pairs. So when we go into that, because these are both parental chromosomes, or as we could put this, they are homologous chromosomes that have sister chromatids, and then they can perform. We're going to be curious if they have any sort of crossover linkage. But before we can even get to that, we need to see what the distance is between these two alleles along that chromosome. So as we start there, we're going to try to see what the distance is here between A and B. So with ignoring who the parental alleles are, or allele genotypes are, we're going to look at what the distance is between A and B. So we're going to eliminate the A and B relationships that are most like the parents. So we're going to ignore the ones that are A and B and the wild in those presumed positions. So we're going to look at ones that are like A plus B. So here's another plus B and another A plus. We're going to add those populations up. So that's 160. And when we take that and we're going to add it all up here, as you can see, and times it by 100, we have the recombination frequency of 18.48. Now we're going to be going down a little bit farther, and we're going to repeat this for A to C as well. And just like before, where we looked at the relationship between A and B, but we eliminated everything that was like the parental genes, we're going to do the same thing with A and C. So we're not going to be looking at stuff that looks like A and C. We're going to be looking at like B plus, but we're not going to be looking at plus plus. We're not going to be looking at AC. So we're going to be looking at these guys and labeling them the recumbent. We're going to add up these populations, and we end up coming up with a comparison population of 2,220. We're going to divide that by our entire population, times it by 100, and we end up getting a recombination frequency of 38.66%. And as you can presume, we're going to do this again with the last combination of the two alleles, which is the B to C. Once again, this guy kind of wound up on 2 pages. I apologize. Let's back that view up here. And so when we do this again, be mindful not to include the parental genotype or the allele combinations that look like the parental genotypes. We end up getting 2,800. We divide that by the entire population. We get 48.76%. And so once we add this up, we end up seeing that there's a little bit of skew in here. So we probably have some double crossovers going on. So we want to see what that looks like. And in order to do that, we need to get a good idea of what the order of these alleles are, because it's not necessarily A, B, C. Like who would give us a problem that easy? That would be just too easy. So we're going to first take our greatest distance here, which is going to be that 48.76%. We're going to lay that out here on this line. So that 48.76 is the distance between B and C. So if you imagine that this line right here, let me zoom in on that for you. If we imagine that this line right here is our chromosome, here is our allele B, this is our allele C, and that distance represented by this block is 48.76. Our next largest distance is the distance between A and C, so that is that 38.66. Fantastic. So we can presume that the order would be BAC with our distance over here being 18.4 because the recombination frequency is equivalent to those mapping units for presuming how far is the distance of those alleles on the chromosomes. So to look for multiple crossovers, we can take this distances and calculate the interference. So, and with the interference, we want to take the two greatest distances, reduce them to decimals, not do them in percents, use the law of products, multiply them together, and we find that we get a percentage of 18.85 as expected for our double crossovers, not couple of crossovers. Very silly of me. However, normally double crossovers are seen as a very small skewed genotype. So we want to see what our expected versus our observed would be. So our smallest genotypes, if we go back up to these tables, our smallest genotypes were these two guys here. So we add these up, so 140 plus 100 would be 240 out of the entire population, which was 5,742. So if we take our observed over expected, our expected was 18.85% of the population. So that would have been 1,082.4 events. So if we do our observed over our expected, and subtract from 1, that would have been 77.82. So the inference would have been very, very high in this situation for how much the double crossovers would have happened. So there appears to be an external interference going on, or possibly something else with this data set going on that probably wherever this came from probably should be if this was dealing with like a clinical trial, would be highly suggested to go back to the drawing board or see what kind of inference is going on. But as far as this goes, that's how we can see where the double crossovers come into. We have identified that these two top ones are our parentals, and then these guys would be our single crossover occurrences. So get him there, get him there, get him there. While these are our double crossover categories. Crossover, I apologize. This is our last double crossover category. And between only 3 alleles, we're not going to have a triple crossover. But of course, if we were investigating a larger a larger genotype that we were exploring, there could be multiple kinds of crossovers. So that is our mapping demonstration. Thank you very much.